Okay, we're looking at binomial distribution today. Right, you should be able to understand the concept of a binomial distribution, okay, as an example of a discrete probability distribution. Okay, the next thing is use your binomial distribution as a probability model, right, including the conditions under which the binomial distribution is a suitable model. Right, and lastly, you need to use the mean and variance of the binomial distribution without proof. Right? Okay, you need the following topics, okay, for you to be able to proceed with binomial distribution. Right? These are some examples of discrete distributions. We have binomial, we have Poisson, we have geometric. Okay, but for your syllabus, we are focusing on binomial distribution. Okay, in the previous chapter, we learned about calculating the probability of an event occurring in a given experiment. Let us consider the following. Right? In this scenario, a brass coin is being tossed 3 times. The probability of getting hits in each toss is 2/3. Find the probability distribution of x, where x is the random variable denoting the number of hits when a brass coin is tossed 3 times. So in this case, what are the values that x can take? Okay, can it take 3 values or 4 values? Right, so if you are looking at the random variable, number of hits when a brass coin is tossed 3 times, okay, we have the following cases. Okay, it can be tail, tail, tail. So in this case, what is the value of x? Okay, obviously x will be equal to 0. Okay, because x denotes the number of hits. Okay, but in this case of 3 tosses, all of tails, so x can take the value of 0. Okay, of course, what are the other values that x can take? It can be tail, head, tail. In this case, x will take the value of 1. Okay, because x is the number of hits. We have 1 hit out of 3 tosses. Okay, so the idea is we can represent, right, the probability of getting hits, right, in this tree diagram as follows. Okay, so the probability distribution can be represented in a table in this form. Okay, there are 2 things that you need. You need the value of x, okay, and the probability that the random variable x can take at that value. Right, so we discussed earlier on that x can take 0. Okay, this will happen when you have tail, followed by tail, followed by tail. Right, so it is 1/3, followed by 1/3, followed by 1/3. Right, so we have this answer here, which is 1/3 power 3. Okay, this can be written in this form. Okay, this is this means your 3 choose 0 means number of ways of getting hits. Right, the next one would mean 2/3. So what is 2/3? Right, so this is your probability of getting a hit. Right, so in this case, there's no hits. It's 3 tails, so it is raised to the power of 0. The last one here, okay, is your probability of getting or tail. Right? In this case, we have 3 tails, so the power is 3. Okay, so we look at the next case where we have 1 head. Right? So with 1 head, how many cases do we have? Okay, we actually have 3 cases, right? Which is tail, tail, head, followed by tail, head, tail, followed by head, tail, tail. Okay, let's look at this from the tree diagram. Right, so when you have tail, followed by tail, followed by head. Okay, the property is represented by 1/3, followed by 1/3, followed by 2/3. Okay, repeat this for the next 2 sums. Correct, we have tail, head, tail. So tail, followed by head, followed by tail. Okay, this is represented by 1/3, 2/3, and 1/3. Then we do this for the last case, which is head, tail, tail. Head, tail, and tail. This can be represented by 2/3, followed by 1/3, followed by 1/3. Right, so if you look at these 3 probabilities, right, they can be condensed to this form. Okay, it can be rewritten in a similar manner as this. Okay, because in this case, right, the 3 choose 1, okay, represents number of ways of getting 1 head, right, out of 3 tosses. Right, and this one is your probability of getting a head. Right, so we have 1 head, so the power will be 1. Right, and the next one is probability of getting a tail. Right, in this case, okay, the probability of getting a tail is 1/3. We have 2 of them, so it's 1/3 times 1/3, which is 1/3 power 2. Right, so we repeat this idea for x is 2 and when x is 3. So if you compare this term to the expansion of this, okay, it's actually the first term of the expansion. Okay, this can be seen in this line here when you have the binomial expansion of 1/3 plus 2/3 power 3. Okay, we can see that this is the first term of the binomial expansion, which is same as the first term of the probability distribution when x takes the value of 0, which is indicated here in the previous page. Okay, this is the second term of the binomial expansion, which is when x is 1, and this is shown in the previous table. So we call this the probability distribution, or we call this probability distribution the binomial distribution. Okay, note that this probability distribution of x, which is the random variable representing the number of heads obtained, can be expressed in this form. Okay, so it is read as probability of the random variable x taking a specific value of x is equal to, right, this form. Okay, where your 3 choose x means number of ways of getting x hits out of 3 tosses. correct? Your 2/3 represents the probability of getting X hits, correct? And your 1/3 represents the probability of getting 3 minus X. Okay, and we mentioned that in this scenario, your X can take 4 values, 0, 1, 2, and 3. Okay, what happens when a coin is tossed n times? Okay, then the probability distribution of X, which is the random variable, the number of hits obtained out of n tosses, can be represented by this. Okay, next we look at the conditions for binomial distribution. Okay, the binomial distribution can be used in situations in which a given experiment, also referred to as a trial, repeated a number of times. Okay, for the binomial model to be applied, okay, we are looking at these 4 conditions. Okay, they must all be satisfied. Right, the first condition is the experiment consists of finite number of repeated trials. In the next one is each trial results in 2 mutually exclusive outcomes, which is referred to as success or failure. Okay, the next one would be probability of a success, which is usually denoted by P, is constant for each trial. The last one is the trials are independent of one another. Okay, so what does independent means? Right, so independent here means the occurrence of one event does not affect the probability of the occurrence of another. In the previous scenario, the probability of obtaining a head is 2/3 when you toss a coin. Right, so when you toss a coin once, the probability of obtaining head for the toss is 2/3. When you toss the coin a second time, the probability of obtaining head is still 2/3. Okay, this would mean that the events are independent. Okay, as the occurrence of any one event does not affect the probability of the occurrence of another. We will use the 4 conditions to explain why a binomial distribution is appropriate for the previous scenario. Okay, the conditions are stated on the left-hand side of the table. Correct? So we will discuss one by one, okay, whether the conditions are satisfied. Okay, so let's look at the first condition. It says that the experiment consists of a finite number of repeated trials. Correct? So what is the repeated trials in the previous scenario? Correct? So we are tossing the coins 3 times. Correct? So tossing the coin is a trial. Correct? And 3 is finite. So the first condition is satisfied. Okay, we move on to the next condition, which is each trial results in 2 mutually exclusive outcomes. Okay, so what are the outcomes when you toss a coin? Okay, so when you toss a coin, there is exactly 2 mutually exclusive outcomes. Okay, so what are the 2 outcomes? Correct, so the first outcome is actually a head. The next outcome is actually a tail. Right? So the tail is also interpreted as not getting a hit. So this is referred to 2 mutually exclusive outcomes. Right? The next condition will be probability of a success is constant for each trial. Okay, so what does this mean? Okay, this would mean the probability of getting a hit is constant for each toss. Okay, because in the previous question, the coin is biased, and the probability of obtaining a head is 2/3. Okay, which means to say, when you toss the coin once, the probability of getting a head is 2/3. When you toss the coin another time, the probability of obtaining a head is also 2/3. Right, and the last one, the trials are independent of one another. Right, so we have explained earlier on that the outcome of a toss is independent of the outcome of any other tosses, because when you toss a coin once, the probability of obtaining a head is 2/3. When you toss the coin again, the probability of obtaining a head is still 2/3.